And I believe we're good to go. Good afternoon, it's good to see you all still around. I was already expecting like, oh, we're getting close to the end, and I see people with suitcases passing by. Think like, oh, they're leaving, they're missing out on this talk. But I'm happy to see you here. Today, this next hour is going to be all about WebAssembly in combination with .NET. I want to emphasize it's a lot WebAssembly security as well, so it's not only .NET. Just a raise of hands, who in this room works with .NET on a daily basis? I think most of the audience are. Yes, you're the right audience. So we're going to talk about technology stacks that you can use on WebAssembly, but that can literally be everything, right? But I'm going to get there once we're going to do some demos and work through all the stuff. So that's cool. Okay, cool. Using WebAssembly to run, extend, secure your .NET application. First, who am I? Introductory slide with a big picture. So my name is Niels Tanis and I work as a security researcher for Veracode. I have a background in .NET development, which I've done for like over a decade. And I moved into the security space where I did security consultancy, some ethical hacking pen testing. And right now I'm combining all of that in my role at Veracode. So you probably know the Veracode does static analysis. And if you're doing stuff with .NET and Veracode, then you should talk to me because that's what I do as well. I'm not going to talk about Veracode anymore. If you want to talk more about us, then come see me afterwards, because today's subject will be WebAssembly, right? And if you go to webassembly.org and if you check out the first, let's say, high-level goals, you'll see that it's a portable binary format that will serve as a compilation target that can literally run everywhere. It's also high-performant and should be really secure by default. So when this was introduced, I think it was 2017 when WebAssembly was 1.0 or something that everybody calls MVP. It was released for all major browsers, so you can run WebAssembly inside your browser. I think the first glimpses of WebAssembly itself was 2015. The people from Mozilla Firefox started out some of the bits and pieces, and it of course originated from some other web components, which I'm not going to spend too much time on. But WebAssembly itself, what happened after this was done? Existing code bases were compiled to WebAssembly, right? So if you take a C code base and if you take a tool called mscripten, which you're going to see in a bit as well, you can compile it into WebAssembly, and AutoCAD has got a version of their tool. I've not run it, I've not seen it, it's just a screenshot I took from the internet, of course, but it allows you to run their software inside the browser, right? So WebAssembly, there might even be somebody from AutoCAD on this conference. I did see it on some of the badges, so maybe they can explain a bit more how it works. But this was a nice thing, right? Adobe did the same with some of their products. And it's all based on mscripten, compiling your C code into WebAssembly and run it. That was the first thing. What happened after that? What else did we see? So WebAssembly was also used as an SDK for SDKs. So both Disney Plus and Amazon have got two really nice blog posts where they explain how they use WebAssembly. Side note, if I'm referring to articles, all of the links are in the notes, and at the end you will see a GitHub repo that will have a notes version of the slides, and you can find all the links inside of that. But the nice thing is that they explained, because you can run near native, you can literally run on a lot of devices. They build up their application and also high performant if you're streaming media, right? You can, if you compile it into a WebAssembly module, it can really be done easily. Both Disney Plus and Amazon do it. And Amazon Prime even allows to be like targeting 8,000 devices all at once, which is, I think, nice. Even the mobile stuff, they reuse it. But you can imagine, like, even if you have Android TV or Apple, or you have some kind of set-top box you got from the cable provider, they all have that client inside, right? And it works, and it's all, a lot of that, it's done because of WebAssembly. So I think this is pretty cool. Technology gets everywhere. And the nice thing is, because it's a compilation target, you can write in a lot of languages. You compile .NET to WebAssembly, which you're going to see in a bit, but you can do Go, you can do Python, you can do Java right now as well. I've seen some stuff from Kotlin over the last couple of days. So it's all getting there, and it's all running on WebAssembly, which I think is pretty cool. So this technology evolved. And I'm going to take a step back a bit. And I want first to dig into some of the security aspects for what makes WebAssembly secure. Because there are certain things inside the language, or like the way it works, that we need to be aware of. Then we're going to run .NET on WebAssembly, which you probably can already imagine what that will be. But we're going to look into some of its internals, how it works, because we need to have some understanding. And we're going to do it browser-based, but we're also going to, of course, pull it outside of the browser. And that's where the fun stuff happens. Then we're going to take that concept and we're going to extend .NET with WebAssembly. So have existing WebAssembly modules executed inside that context, and then also focus more on security aspects of it, because there's a really rich layer of security on top of it, and we can leverage that, and we can take care of some security problems that we face. At the end, it's going to be concluding Q&A, as I said. So, WebAssembly. If you look up the design, they had the goals of be fast, efficient, and portable, right? So near native speed across different platforms. That was the exact reason what we saw with Amazon and with Disney+. Readable and debuggable. So you have a bytecode, you can open it up, you can look into it, but there's also textual representation. And I'm going to show you that how it looks. It's not that it's like readable. You can easily see like, hey, this is where the problem is. No, but you can read it if you want to. It wants to be secure, keep secure, because it's run inside of a sandboxed environment. So running inside of a browser, same origin policy helps out, of course. But if we take it outside the browser, we need to do different things. And it was not supposed to break the web. I believe it's the case, but of course with browsers and everything that's happening, compatibility needs to be guaranteed, right? Because if it breaks the internet, then people are not using your browser anymore. At least that's what we've seen with all the browser wars. But backwards compatibility is also really important. So as I said, it is a binary instruction format for stack-based virtual machine, which is like similar as .NET MSIL, right? The CLR runs MSIL. It needs to be a portable compilation target. And one of the additional security models they have is we want to protect users from buggy or malicious code. And we want to provide developers also with helpful primitives. And what they mean by that is it should be pretty intuitive to take the right path. And if you need to do something bad, then hopefully the API is really explicit, or the compiler maybe even tell it to you, say like, hey, what you're doing here, it might be a risk, or consider not doing this because it might be harmful. I think that's the default path should be straightforward, easy to use, and secure. So a lot of design aspects, but what makes WebAssembly secure? So each module within the WebAssembly ecosystem has got a piece of memory, WebAssembly memory, and it's isolated per module that gets loaded, right? So it's a chunk of, it's like an array of data, and it will be used only by that module. And if data needs to be shared across other modules, then you need to do something for it. So by default, it's just an array of bytes, and the module can manipulate that. A module itself, of course, might have got security issues, which allow you to mingle with that memory. So there's still a possible way of doing stuff that might be unintended. So on top of having this kind of linear memory, there's an additional security aspect of WebAssembly which we need to be aware of. And that's something called control flow integrity. And I was thinking about this when I was creating this presentation, like how can I explain this in the best way? Because there are some really good articles that go deep into how backend compilers deal with this. But let's say this is a code snippet that we see over here. And what control flow means is like, what are the logical paths within my code that my code can follow, right? So in this case, we see that we read a read line from console that gives input. Somebody types in a string, we're screwed. But if somebody types in a number, we can say, okay, this is the number that you put in. And then we're going to have two conditions saying like, hey, if number is greater than 5, put it down, the console write line, and saying it's larger than 5. Otherwise, let's say it's smaller, and then we're done. So this is an execution. And if we translate this to a graph, it may look something like this. Right? So we have the first part that executes, that will always execute, taking the number, writing it out, and then we get up at the decision, saying like, hey, if number is greater than 5, we're going to take this branch, otherwise we're going to take the other one. So what control flow integrity does, it has a map of these kinds of executions within your app, and it will instrument your application. And if at runtime something occurs that breaks that path, then it will panic and it will stop, right? So that should mitigate, that's the right word I need to use, some of the problems you might have if a module mingles with its own memory. So we can safely say it's pretty secure how it works in this way. So it's mostly compiler stuff that helps us out. So this makes WebAssembly, in let's say from technical perspective, how it works, pretty secure, how the instructions are being processed during runtime and so on. One really cool project that leverages WebAssembly is something called RLBox. Who in this room is familiar with what RLBox is or has seen it before? It belongs to Firefox. It's the Firefox team that created it. So when running a browser, you rely on a lot of plugins that take care of media stuff that gets rendered, fonts that gets rendered. And what the team at Firefox did together with, I think, with the university, is that they looked into a way of taking those libraries, compiling them into WebAssembly, so taking C code, probably Emscripten, to convert them to WebAssembly. And then you have some guarantees that the things that I just explained to you, so if there's like some unmanaged, let's say overflow, that kind of thing, like the basic security problems, that would have been taken care of by the WebAssembly stuff itself. So if you would then run that plugin inside the browser, it will be safer. But the only thing that they didn't want is they didn't want to have WebAssembly embedded inside the browser. It probably was high performant or it was good enough. But then they decided to take that WebAssembly and translate it back to C code and then put it in the code base. And then compile it all at once, which means that you take some of the security aspects you get from WebAssembly and then put it inside the browser. And the other thing, and the additional thing that they did is they also created a programming model that if you do this with a plugin, you need to, when you're writing the software, you need to explicitly validate the data that comes back from the plugin. So it's like helping out the developer saying like, hey, you run this plugin, data comes back, you need to have a validation routine in order to take care of the data before you process it. And I think that's a pretty strong model. I'm not sure if people were in my talk last year on sandboxing.net. Some of the aspects, this is the ultimate concept that I want to implement on that same area, because I think this is quite powerful if you can like help out developers doing a better job. Next week I will be in NDC London talking about that, and once the video is there and you're interested in it in combination with .NET, look into that one. But at our box, right, as I said, because WebAssembly in its way how it works is pretty secure, they use that, they leverage that in order to get it into the browser. So that's, I think, is pretty cool. There's one really, I think even two really good talks done at Black Hat on this from the people who created this. You should watch that. So getting back to what do we need to do in order to get .NET running on top of WebAssembly? So this is a conceptual picture that I took from a guy called Ivan Tolson, who is with Fermion. He works on Spin, so look him up. But he did a talk on .NET and WebAssembly as well. And he created like this picture where you see like, hey, if we have a .NET application, it consists of user code, which is IL. We have a base class library that we use. We have an execution engine, which they call WAS, which will be the CLR that starts it all out, right? So if you start out a process, the CLR will take care of bootstrapping the stuff. It will start out and then it will run your app. And that, of course, all runs on top of your host. And how can we run WebAssembly on top of, or how can we run .NET on top of WebAssembly? We can replace the execution engine with one that's based on WebAssembly. So, and of course, we need to run it inside the browser, right? And where have we seen this concept? Of course, that's with Blazor WebAssembly. So what they've done is they've taken parts of the mono runtime, which you see, compiled it into WASM with Emscripten. There's a lot of other things included as well. There is a JavaScript bridge that takes care of some of the mingling because you need to interact with the browser, you need to have access to the DOM, and so on. But the .NET WASM itself will have the framework, and there are DLLs, right? So this is the basic thing. Let us quickly create a project to see what type of things we get streamed in order to fully understand, right? So let me do this. First, let me create a quick Blazor app. Let's say .NET run. Starting it out, right? So it's just default template, nothing fancy. I want to make sure that I have this one running. Let's clear it all out. Looks good to me. So now if we open up, we will see this is the default template that gets executed. And if we then go to the thing that we see over here, which is network, which view am I watching right now? Not the right one, I guess. Let's do this once more. So, of course, what happens is that the browser will start downloading the basic stuff of WebAssembly. So it will download first all the DLLs. Let me do it once more, because I might have been some caching, right, involved. Did I stop the other one? Hold on a second. Probably did not do that. And it did not have the tools open. Okay, cool. So if you have run this before, and I'm just going to skip this for now because I'm just going to like go back and forth within the screens, but you will see that it will first download all the DLLs, right, the .NET application. At the end, it will have .NET WASM, which is the CLR implementation, and then it will start the .NET application. It will run those DLLs inside of the browser. So the other thing, it's of course there's a performance penalty, right? If you look into it's kind of interpreted, right? Because it runs a virtual machine inside of a virtual machine. That's at least the quickest way. They did do some optimizations with the last .NET release. Some people were expecting that the full .NET stuff would be emitted into WebAssembly. That aside from the fact that it increases the size really big, it's not performant because some features are not implemented into WebAssembly, like garbage collection and so on, right? So there are some difficulties. But this allows us to have a CLR that runs DLLs inside the browser, and the JavaScript files will help out doing some interactions with your system. So keep that in mind, because that's the first concept on how to run .NET. Because what do we need to do if we want to take this outside the browser? So we still have a need for a host where we can run on, which in this case is not the browser but the machine, and we want to have the execution engine still run WebAssembly. And what do we need in order to do this? And that's something called WASI, or WebAssembly System Interface, right? So in order for us to interact with a system that's not the browser, we need to have some kind of abstraction available. And the nice thing about it is that it's taking care of all the basic stuff that we need. And it will make sure that it's a POSIX-inspired, engine-independent, non-web system-oriented API for WebAssembly. And the other thing is that it was introduced in 2019 by Bytecode Alliance. So Bytecode Alliance is a cooperative thing between big companies like Microsoft, Fastly. They all help out. They created this standard to say, like, hey, if we have WebAssembly running on this and we want to interact with system like files, sockets, everything we need, standard input, standard output, it will look something like this. And they also said, okay, we're going to do runtime, which is like responsible for running the WebAssembly, called WASM time, in order to be guiding us through like as a reference implementation. So it's a strong sandbox with capabilities-based security. So we're going to dig into it a bit further, but if you have the whole system model of things you can access, and if you can then flag access and say, like, hey, you're not allowed to do this, or you're not allowed to do that, that can be pretty granular, pretty strong, right? So a .NET application will start out in its own process if you start it on your machine. And it will have access to all the things the same process has access to. And this is like an additional layer on top of it. It will give us more control, right? So it will say, like, hey, are you allowed to write these files or read these files? And there also will be future support for sockets, for other things like sockets are random, like other system access. That needs to be, like, it's in the making right now. I will get to that at the end of the presentation. And it's almost similar like to .NET Standard, right? We have all, if you've been active in .NET at some point, we had the converge from .NET Core and the full framework. .NET Standard was introduced to make sure that those two BCLs got together. This in some way is familiar. So how strong is this WASI concept in general, if you look at it, in combination with WebAssembly? It's as good as this guy tells, Solomon Hykes. So he was the founder of Docker. And when WASI was first talked about, he mentioned in a tweet, like, hey, if WASM and WASI existed in 2008, there would have been no need to create Docker. Which, of course, is quite a big statement to make if you were the person that started out Docker. But he says it's the future. Next day, after he's done this tweet, he came back. He says, like, so will WASM replace Docker? He probably got some angry phone calls or people pinching him, or I haven't seen the full thread on Twitter itself. But he says, like, no, but it cannot replace, but it can be a good addition, right? And it might be something that lives next to each other, like side by side. And what have we seen over, let's say, I think it was fall, October of last year, is that they introduced Docker's capability of running WASM assembly modules. And in this case, it uses WASM Edge, as you see on the right-hand side, to execute the modules. the things we're going to do are all focused on WASM time, but WASM Edge, it's just a runtime that allows you to run WebAssembly that is aware of WASI as a whole, and it can execute stuff. So this is pretty cool. So if we want to run WebAssembly outside the browser, we need to have this. We need to replace the host with a WASI capable interface, and in this case, in our case, it will be WASM time. So we're able to run it. And I think it was built last year when Steve Sanderson introduced a conceptual experimental WASI SDK for .NET that he created, which will take your app, which will create a single WASM file that will use system interface, the WASI, the SI, and it will execute. So let's go to an app and let's see what is it, right? So keep in mind that we saw that Blazor did download everything. And now we're going to move to a console app, and we're going to fiddle around a bit how it works, and then also look into some of the capabilities we're able to limit. Console WASI, yeah, that's the one. So it's minimal. It's a console app, single line, contains a write out which says like, hey, this is the OS architecture that you run on top of. You probably have seen the same demo with Steve if you look into it. What do we need to do in order to get this running on WASI? We need to make sure we have WASI SDK included. And this is a preview. I think it was released or published 2 weeks ago. So keep in mind, all of these bits are preview. And I was wrapping up and making sure I started it out. And on Monday, I pulled everything in, looked at it, was still working, so that's cool. But it's work in progress, which is a good thing and a bad thing. We will get there as well at the end. But this is the thing. So if we now say we built this, and if we then go to bin debug 5 and look what we see here. Am I in the right folder? No, hold on. This is the right folder. So what we see here, we see a console app.wasi. If we just say like, okay, this is the default executable we get that will run on my Mac. If I run it, it will say like, hey, hopefully you can see it, it's at the bottom. Let's maybe scroll it up a bit, but we see that it says like, hey, welcome from ARM64, right? Maybe do an increase. What if we take the WASM one? We will see exactly the same, and it will say, okay, now you're running in a WASM context, right? So it's not running directly on my machine, but it's running on my WASM time. So even if you have this SDK installed, you can say .NET run in your main project, and it will also do WASM. And it will say like, okay, what's happening here? Underneath the hood, it will start WASM time, and it's only tied to WASM time to execute, but it will do exactly the same. So this is the thing. We've seen that there are different architectures, and also I said something about size, right? If we do an LL here, we will see that we see console itself, which is an app, pretty minimal, 145K, probably relies on some shared stuff that's on my system, right? This one is 8.5 megs. But the problem is that it will do exactly the same as we saw with Blazor. That was the reason why I showed you that example in the beginning. It will put in all the DLLs embedded. There is a WASM file that will bootstrap the CLR, and that will then start out the app, right? So that's the difference, and that will be run on top of WebAssembly. So keep that in mind. So that's how it works internally. So what are the cool things that we can do? Let's open up the file. Now we're going to do some code. Let's say I want to open a file in WebAssembly. Let's say, and that will just be simple. So let's say I want to read the content of a file, which in my case will be file read all text, and then say we're going to read hosts file. And then we're going to just easily say write line content. We're just going to take the content of that file, which is my etc host, which is in my system, and then have it write out, right? So .NET build. If I'm in the right folder, hold on. So it has built. So what if I now do the default app? So this is my ARM6 one, right? It runs on my machine. We will see the file. if I say .NET run in this folder, it will do the WASM time equivalent, right? What will happen then? It will give a really obnoxious big error. But what it tried to do is it tried to open a file that it was not allowed to open. And that's the whole, like, as I said, WASI capabilities type of thing. And WASM time right now puts out this error. There are some implementations on other runtimes that are more descriptive. But it will show us that we're not allowed to do it. And in order to get there, we need to instruct the following thing. So I'm going to say to WASM time, the directory you're allowed to read, sure, hoping that you're able to see it, and I already executed it, but the directory you're allowed to read, you just give it the folder and pre-open the directory, and you will hand over the handle to the WASM time, and select you're allowed to read it. And that's exactly what happens then. And if we then open it, we say like, hey, we have run this in the WebAssembly context, and we were allowed to open the file, right? So this shows us the WASI capability of file system, and because we instructed our runtime that it's allowed to read files from that other location, we can do it. By default, it's not possible. I think that's good, right? Talking about having a good default and then explicitly granting access to stuff, that works out. As I said, it's still in the rough. Are you going to use it? Probably not, but let me get back to the slides because there's more to that. It was experimental. That's also what Steve Sanderson says in his demo, like there's no guarantee we're going to do this. I think WASI has a really good path forward, so I'm expecting that they will do something about this. And I was talking to some of the .NET people in October, and they pointed me out to this issue, which was created by Steve Sanderson after he created its demo, where they state like, hey, we're going to support some WASI, and some of the fixes, some of the bug fixes for the SDK has been made and have been made available already. And I'm looking forward to the first preview of .NET 8, where this probably will become better or will improve. Still no guarantee that they will do it or if they will release it, but at least they're working on it, and that's nice, right? So this allows us to run .NET on top of WebAssembly outside the browser with the help of WASM time or any other WASI compliant runtime, right? I think that's pretty cool, and we're allowed to limit file access and so on. Now we need to get more advanced, and I want to move forward in moving to, hey, what can we do in order to extend .NET with WebAssembly? And with the whole WASM time runtime, there's also a WASM time .NET NuGet package that will allow us to run WASM on top of .NET. And it allows you to run, it allows you to run any, let's say, arbitrary WebAssembly module. The only constraint it has, it needs to be compiled against the WASI stuff. But you can write it in Rust, you can write it in Python, you can write it in Go. And that's exactly what I did. So let's move on. Let's go back. We're going to quickly peek into some Rust code, which is the module that we're going to use, the WebAssembly module that we're going to pull into .NET. And then we're going to run. I'm going to open up this one. Let me collapse it, make sure that we're in. So now you're going to get a crash course Rust, which is not the case. But so WASM time itself is also written in Rust. And the language itself, I'm really a fan of it. I'm working with it a lot lately. This is, of course, just a demo I took, which was already there. But what it does internally, there's like, it almost looks like a console app within .NET, right? There's a main that will accept arguments from the command line. The arguments are going to be passed on. And then it will say, okay, let's do the process of those arguments. And what it does internally in this, it will take one file from source to destination, it will copy. So we're going to mingle with files again, right? Including with WASM time. But now we're also going to include this inside of a .NET application. So it's pretty straightforward, nothing fancy here. It will build. We can do that right now. I'm going to say cargo build. It's instantly done because there's cache, the file's already written, so it's there, that's good. Now let's move to the console app because there's a bit more I need to explain in that one as well. So as I said, in order to execute WebAssembly, we need to have the runtime available, and that will be the package. And you can just easily do the WASM time package and add it. And WASM time itself was released 1.0. They quickly, released a couple of other releases on top of it, but it's definitely something you could start using. If we look into the program itself, then we see there's a lot of stuff happening. First, we need to instruct our runtime, what we are allowed to do. And I'm going to just redirect some of the output to files in order to see it, because it's going to be a separate thing that runs, right? I need to pass on some arguments, and then at the end, the passing args I'm doing, those are the arguments I will pass on to the Rust module to execute, right? Because I want to copy file A to file position B. Then we need to do a bit more about, we need to have an engine that will run the WebAssembly itself. There's a linker that will take care of the type resolving and where stuff originates from. And then there's a store that will be used to run and get the data in and everything that's available. We're saying, okay, we want to run in a WASI configuration. We're loading the WASM module from file. We're going to instantiate it. Then we get a function back. And then we can invoke it, which is a lot of code. Yes, I know. But this is the basic concept, and the future of this, you're going to see later on how this will work. But the nice thing about this is that if we run this, let me make sure I'm in the right folder. So if I say .NET run, we will see hello NDC Security, nothing happened. Okay. If we look into the error log that's been written out, we will see that the Rust module, this was one of the arguments we saw in the Rust module, says like, hey, you want to do this, and you want to do a copy from to, but you didn't provide any arguments. That's exactly what we did, right? So that kind of works. So now say .NET run, let's say we want to do A to C/host again, the same file, and we want to copy it locally and say it's host. It's still verbose. If we look into the error log again, we will see that it complains about the fact that it cannot open ATC host because it's not a pre-opened file descriptor, right? So this is the exact same things that we saw before when we were doing the WASM time console, but now it's programmatically done. So we need to instruct that it's allowed to read files. And this is exactly like the whole, I want to make sure that it opens a directory, and you can even map stuff. So let's say we're doing a map from etc to etc, same way. Let's get rid of the trailing slash. I've never done that. Probably it will screw up. And then that's the default one, but we also need to grant access to the local folder. Otherwise, it's not a right. It has no right to write the files to our system as well. So as I said, it's pretty explicit, right? You say like, hey, I'm not sure how I want to be bothered, but if you look into the whole component model, which we're going to talk about later, you will see that it will fit in, and you will have descriptive stuff happening. So right now, we have changed it. We say like, okay, you're allowed to read from etc, and you're also allowed to read and write from both directories, right? So let's move back. Let's say .NET build. And now do the .NET run again. And if all goes well, which happened, we see that over here, there is a host file that's being written and it's being copied to this local system, right? So this gives us, again, access to what type of files is this module, what type of parts of my file system is this module allowed to access. And you can also read out and say, hey, I want to say this is etc, but it will be a subfolder of my current run folder, right? So that's almost like a container that isolates stuff and so on. So pretty powerful. That's cool. This is only related to file system. What else could be wrong with a module, right? And get back to the first slide where we talked about designing of WebAssembly. They want to safeguard end users also from malicious modules. So what happens if a module is hacked or its supply chain is compromised, which is a totally different topic, of course, but it does a lot of compute. What else can you do in order to control the amount of compute that a module can execute? Within WebAssembly and within WASI, there is a concept called fuel. And each step within the engine will take one fuel. And it's just like, it's not that it's tied to a specific amount of cycles, it's just a logical unit that they use. So in order to do something, at the end you can say, okay, this will take 10,000 fuel. And if it exceeds 10,000, then we might be better off stopping the thing. And that's exactly what you also get right now within the module. So we need to instruct the engine that we're going to deal with this based on fuel consumption. And we need to make sure that once we turn it on, this is the budget that you get. And it's as conceptual, even the host can decide to consume fuel if it feels the need. So you can even have a dynamic system saying like, hey, I know that this module will take up this amount of ticks in order to, like fuel, in order to complete. I have more control of it. And that makes it less prone to, let's say, a module that has become malicious and that does a lot of things. Maybe somebody decided to install a crypto miner and is doing stuff with that on your machine. That takes a long time. So let's just quickly delete this file. Move to trash. Let's move, and let's say a .NET build again. Did I save it? Just close it just to be sure. .NET build again. If we run it right now, you will see at the end, I added an additional console write line, which is like the best way of programming, right? Console write lines. But it will show us the amount of consumed fuel, which is in this case is 35,000. So let's say after a couple of runs and you know a module should be able to complete its stuff within that amount. Let's say we limit it to 20,000, or let's say to 5,000. What will then happen if we build? Again, did I save? Did I close? I'm just going to be neurotic because of the demo gods. And then say .NET, what we did before. It will give us a cryptic method saying like, hey, it ran into a trap. And this is the trap is the way of the WASM runtime saying, I'm stopping this execution because it takes too long. So that's a way of view of limiting what a module is allowed to do. So that will give you more control over what it's allowed to access and also the amount of things it can do based on that fuel, right? So I think this is a pretty powerful concept. And yes, code is a lot of things you need to do yourself, but we'll get there at some point. I will explain what will be the next path forward. So we've done all of this, and let's say we have a WASI module that we have compiled against with C# or Rust or anything else. One other cool thing we can also do with it is something called trusted computing. And trusted computing can be based on the following threat model. This is one from XKCD. You probably know this. Jimmy drop tables, there's one on supply chains, like the one with the big pile of rocks, and the one in the bottom is maintained by a single person. But this one explains like what type of layers do you have inside your modern stack that might be compromised by a customer, compromised by Bitcoin miners, compromised by your government, and so on, right? You can just like literally say, hey, every layer can be compromised. And the cool thing about it is that there is a project called Enarx, which is started out by a couple of people who came from Red Hat. It's a company called Profian, also part of Bytecode Alliance, and they decided to take confidential computing with WebAssembly. And what they do is they take so-called Ts, which are trusted execution environments. That's a part of your CPU, and it's not a TPM; it's different. But it allows you to take a WASI-based module, which we have seen we can write in .NET, we can write in Rust, we can write in everything, and we can run it in a trusted way. Because what Enarx does, it will have the following threat model. It says like, hey, I don't trust the host it runs on. I don't trust the host owner. I don't trust the host operator. I want to make sure that the hardware I'm running on is cryptographically verified. And I want to make sure that software is audited and before it starts, and cryptographically verified as well. So can you imagine that you have confidential data of, let's say, customer or crypto, let's say, or something that needs to do compute in the cloud? If you do it on Azure, AWS, Google, you rely a lot on their hypervisors and everything that's underneath that, right? But you might not want that data to be visible on that system. And this might be a way of dealing with that. So what Enarx does, it takes the T of your processor, which in AMD is the SAV, and Intel has the SJX, which is all acronyms, and then IBM has the PEF. But it will do all the attestations that I mentioned. So once it starts out, it will check the crypto of the processor. It will check its origin, right? There's a root of trust in the hardware. And then it will have instrumentation saying like, okay, if I'm starting out Enarx itself, I have a runtime that's responsible for encrypting the workload and pushing it onto the processor. And that runtime is open source. Everybody can see it. It can be audited. And the other thing that they do is they also do attestation of that, like how long does it take normally to start out? So those are all indicators. And if it's all green, then it will decide to run, right? So that will all reduce the risks that you're facing if you're running stuff on cloud, for example. I can also run this on my system, Enarx itself, but what happens then underneath the hood? It will just take WASM time and run it, right? Because that's in essence what you're doing. Only if you're running this on Enarx on a system itself, on a hardware, it will be done on this part, right? Where WASI will run on top of the WASM runtime of Enarx, and it will eliminate that, right? So this is pretty cool. So I'm not going to bother you with Enarx.wasm and run it again, because that will be exactly the same. But I think this is cool, because this shows that WASI has a good future and allows us to compile every language we just use and have trusted computing. So I'm expecting a lot of this, of Enarx. So keep an eye out on that. So I showed you a couple of things, and I showed you code, which was pretty, let's say, verbose and all the stuff you need to do, all the errors you get, like how can you make sense of it. So what's next for WASM? What do we need in order to be successful with this concept? And there are probably also stuff that we know from the past, which is analog to this, and why would this succeed and why some of the others failed. We will get there. But so the cartoons you see over here are so-called code cartoons. They are created by Lynn Clark, who used to work for Mozilla. Right now she's with Fastly. She still does a lot of work for Bytecode Alliance. And she has some really good cartoon series on how to explain stuff. And she also has some of the things on WebAssembly. So if we look at the code base itself right now, if we write our software, 80% is other people's code, right? That's a statistic that we also once have seen within our reports that we create. So we rely a lot on others, right? And if we look at dependencies, keep in mind, like let's say this is an application that starts, the top one is the one that's responsible. Let's say it's a .NET process that has different modules underneath. Then the top one has access to everything, right? System resources, and it will pass on the keys just to the lower parts. So like, hey, if you want to have access to this, you can do it. If you want to have access to that, yeah, that's fine, right? Somebody else's dependencies can just reach that right away. What happens if a module becomes malicious, right? Whereas a mask, it has become malicious. It says like, hey, let's take a peek at your file system. It can still do it, right, in this context, because there's no safeguarding of not allowing it to do, right? What if there is a vulnerability in the module? That's the side person that talks to the module and says like, hey, could you just give me more system information or whatever, right? So because it's all the same context, it has access to the same resources, they all have the same keys. This is a problem. What can we do to safeguard this? We could do process isolation. So if you look at, let's say, browsers, Firefox, Chrome, each tab, and there's probably some more detailed information on this, but I think each tab mostly has its own process of rendering, right? Because they want to have isolation. You don't want stuff to talk to each other. And in order to communicate between process A and process B, you need something like an inter-process communication or a process boundary, IPC call. And that's exactly the pipeline you see underneath. But if there is two processes, the biggest benefit is that memory is isolated, as it says, but there is a lot of heavyweight around it because you need to start out two processes. And it would have been better if we were more minimal, right? So there's the big process with two modules, slower communication, a lot more overhead. And the disclaimer at the bottom says this is not drawn to scale, just to illustrate. And the one at the bottom, there's like something called WebAssembly nano-process. And that's the next thing we're going to talk about. So it's much more minimal. Each module has its own memory in order to execute. So what can we do to be more successful in this? The memory, the nano process itself allows you to sandbox, right? So if there's a module loaded, there's somebody who's in charge, the head, that will say, okay, this module is allowed to that folder, as we have seen before. Like you can access this folder, or you can do this call on the system, get random, right? Or it can access the clock, or it can do the USB makepad. There's different ways of dealing with this, but there's somebody in charge that's on top of this. What else is more is important? Each of the memory sections that belong to a module will be limited as well. So this module cannot access the rest of the memory unless it gets help of somebody else. And that's where interface types come in, right? So you need to describe how data looks, and then module 1 can ask, hey, I would like to have access to this piece of memory, can you give it to me? And there's somebody else that will then take care of it, right? So modules itself cannot access memory on their own. They probably can with the help of, but it's not their decision to make. And that's the process of interfacing types. But because you still want them, there is data that might needs to be exchanged, right, between those two modules in order to do something. That totally makes sense. But you don't want them to have direct access. And on top of that, we want to have an API with fine-grained permission model tied to it, right? So the WebAssembly System Interface with descriptive stuff tied to it, saying like, you're allowed to do this, you're allowed to access this folder, you're allowed to do this socket, you're allowed to reach out to that one. That will then eventually become the WebAssembly nano-process. So, and what they envisioned in this concept is there is a main module that will be in charge of everything, and that will hand out all the things, and it will help out, and it will eliminate. If a module becomes malicious and wants to have more access, it doesn't have it, right? It doesn't get it because the right is not there, and that helps out. So I think this is pretty cool. And how far is it? So last year, I think it was October, November, there was Cloud Native WASM Day in the US, and there's a real good presentation about the component model, which is the whole ecosystem I just described to you, done by Luke Wagner. He used to work for Firefox, he's with Fastly, you can already see the trend, what the people were doing. They are working on the whole component model, on how the security model should look at, and how you then also need to have tools in order to do stuff, right? Because that's also the thing you're missing. You're not going to glue stuff together with code as I just did, right? It needs to be more automated. But this is a real good presentation if you want to see it on what's the path forward. And he's also a person that was involved with the initial standards of WebAssembly, right? So he really knows what he's talking about. And there's definitely some really good talks at the WASM Day if you want to see more. Looking back at .NET, you probably would say like, hey Niels, we've seen this before. DCOM, yes, but the first thing that Luke says during his presentation is like, it looks like DCOM. Yeah, but we're not doing any distributed stuff. It's mostly next to each other, close to each other. And if people want to do distributed things with this, it's relying on the runtime, on the host where it executes in, right? So that's not a responsibility. And the whole capability-based model, we've seen it with code access security, which is like, I have this book, like a thick one, when I started out my development career. There's so much complexity in what you could do with code access security. I'm not sure if any of you used it. Medium trust and ASP.NET Core, at some point we got that. It turned out just to be a mutex in user space memory that you can flip in order to turn it off, right? So it's really easy to get around it. And that's also the reason why Microsoft says, this is not working, we're gonna limit it. But this is technically similar concepts, right? And I think that's why I really am fond of this, and I'm keeping an eye out like how WebAssembly and how the component model evolves. Because it all relies on how the tooling gets built and how it is. So I see that I miss out on one slide that was supposed to be after this one. So in order to do better things with WASM and with the interface types, there's a tool called with BindGen, which is also done by WASM Time team. And that's a tool that allows you to generate all the plumbing code you just saw me create, right? So it will have the ability to see an interface type saying like, this is a module, it needs to have access to this folders, it needs to create sockets, it needs to do access to random or to other system resources. That's the thing you can then generate host code for and guest code. And if you look into with BindGen itself, you will find that there's already demos fully working with Rust. I think Python is working as well. Unfortunately, not .NET. I hope that they have the demo included, but the tool eventually will also support .NET. I think that's the goal, right? So the glue will be there. But if we then recap and see all of this and say like, hey Niels, it's security. Yes, it looks kind of, there's a lot of output, but how secure is it really? I think in general, we need to make sure that the whole system and how this evolves depends on how secure the runtimes are that execute this. And if you look at the stuff that was published at Black Hat and DEF CON last year in August, every talk around WebAssembly was about fuzzing runtimes and about faults that they found in implementations in runtimes. So that's still applicable. But let's just assume that everybody does a real good job. And if you look at WebAssembly and WASM time, they have a real cool blog post on the Bytecode Alliance, published in September 2022, where they explain how they approach security within WASM time. It's written in Rust, so it uses control flow integrity as well, right? Because parts of the WebAssembly compiler stack also has it. It's based for Clang, which is a backend compiler. And they also have continuous fuzzing, they have formal verification of like, does it really do what it needs to do, that kind of thing. And they have a whole process around security and vulnerability disclosure. So they're pretty transparent, right, in the open. This is a real cool blog post if you want to know more about how it's being built. But as I said, the disclaimer we need to be aware of is it's as secure as its runtime. And then it will stop. If we then look at the conclusion, I think if we look at cloud native, we even saw serverless functions already perform like WebAssembly payloads, right? Cloudflare does a lot of that as well. I think it's here to stay. And also with Docker and WebAssembly modules, it becomes the next thing aside of it. It's minimal. It's much smaller, right? It has less to carry than a full Docker container that contains it all. So it has a lot of potential to be used to run and extend your .NET application as soon as the tooling gets in place, right? Because I think that's also what you saw with Code Access Security. If the complexity of that kind of thing is too big, then how could you even expect people to expect it, like to use it in a good way? And the thing that is key, that's the last bit, I like the whole top-down approach that Bytecode Alliance is taking. Right? So Code Access Security was just there, and it was there to use, and it was the big booklet you need to look through. They're just working down examples on how you can effectively use this, and then they build it up from there, right? So that's why the demos might look a bit rough, but they said like, hey, if people start using this and give us feedback, then we can build something that's valuable. That's the goal. I think that's pretty cool. And keep in mind, WebAssembly runtime is as secure as its implementation. So with that said, I'm going to open up with enough time left for questions. So the first repo contains the slides and the demos. You can reach me on Mastodon on the third link. On my blog post, I'm going to say Tak, thank you. Tak, that's the right pronunciation, right? Tak. Hope you enjoy the conference. Hope to see you maybe next time. Unless there are questions, I'm here until the end, so please feel free to ask questions. And if not, then I'm just going to say I'll let you go and say have a safe travels back and hopefully see you next time. Thank you.